Greetings everyone, and welcome to week 15, which is our last real video lecture. This week we're going to be talking about logistic regression, so let's get going. So to review with OLS, right, we fit a line, right, you see the blue line through this cloud of data, right? And we try to minimize these errors, right? We're trying to minimize these errors. And this is with a continuous dependent variable, right? Along our y-axis, this is a continuous dependent variable. But what happens if we instead have a binary dependent variable? A binary dependent variable. Now, binary means it takes on only two values, in this case 0 or 1, right? So what we can see here is we have some values down here that are 0 and some up here that are 1, right? And we have fit a line to it, right? We've used OLS to fit this data. The problem with this is that in some cases, right, we see here that it's predicting out of bounds, right? If our dependent variable is only taking on values of 0 or 1, in the case of our line of best fit, you can see that in some cases it's predicting values of like negative 0.15, or up here positive 1.15, and that's problematic because in our dependent variable it can't exceed 1 and it can't be less than 0, and yet our line is predicting as such, and that is concerning, right? We have lots of dependent variables though, just like this. So for instance, vote or didn't vote, right? This is a common one in political science literature where we ask people in the previous election, did you vote or not? We also have things like whether someone went to college or didn't go to college, right? Didn't go to college being 0 and going to college being 1. We also see a lot of binary dependent variables when it comes to medical literature, right? Did the treatment work for this individual? Did the medicine work for this individual? Is their disease cured, right? Or is it not cured, right? So in the case of it's cured, that's 1, and in the case of it's not cured, that's 0. So why should we use logistic regression? Because it predicts that outcome that takes on only two values. It can help us predict the outcome that takes on only two values, 0 or 1. You'll notice here this curve, this is essentially the line of best fit, or in this case, a curve of best fit, right, through our data. And it's not sort of exceeding the bounds of our data, right? It's not saying there is a predicted probability of negative 0.15, or in this case, a predicted probability of 1.15. We're only seeing estimates within the bounds of our two datas. Our two values, excuse me. So in this case, this curve was predicted using maximum likelihood estimates. So that's essentially a curve where the observed data is most probable. This curve tells you the probability of the respondent voting or doing whatever one is. So down here, let's say that this x-axis is years of education, right? And so over here is people with low levels of education, and over here is people with high levels of education. And the probability for someone with, say, 6 years of education voting is fairly low right here. It's probably around 5%. So someone with low levels of education down here has a predicted probability of 5%, a 5% chance of that person voting. Now, we move up here, say there's an observation right around here. This person has 11 years of education, and their predicted probability would probably be something like 40%. There's a 40% chance that this individual with 11 years of education is going to vote. Now, moving up here, let's say these people have 17 years of education. Up here, the predicted probability is a bit higher, right? We see the predicted probability in this case is probably somewhere closer to like 99%. So in this case, we see a predicted probability of someone with 17 years of education being around 97%, right? So this curve here helps us tell what the predicted probability of someone with these characteristics along the x-axis voting, right? Or whatever takes on the value of 1, okay? So the nice thing about multivariate logistic regression is it's just like OLS is in that you can include lots of independent variables. So you can include continuous ones like age and years of education, but you can also include categorical ones like gender and region. So whether perhaps the respondent lives in the South or the Northeast, right? That's really the nice thing about it is it's very similar to OLS and what it can do, but you just interpret the results differently, okay? You just interpret the results differently. So how do you interpret the results? First, something to note, you cannot directly interpret the coefficients, and you should not directly interpret the coefficients. Please do not do that. It is bad. It doesn't make sense. Instead, what you do is you calculate predicted probabilities. And that sounds really complicated, but when we do it in lab, you'll be like, phew, that's not too bad. All you'll really do is you'll plug in values for each of your independent variables, and it will sort of spit out a predicted probability. The reason that we have to plug in values for each of our independent variables is that the probability varies across values of your independent variable. So here you can see that going from 20 to 30 minutes of reading, right, has sort of a low slope. A 10-unit increase here has a low slope in increasing the predicted probability. But up here, right, moving from 60 to 70, right, it's the same unit increase in the number of minutes of reading, but you're seeing a much steeper slope, right? So all that we're going to do in the lab is plug in numbers, and it's going to spit out predicted probabilities, and we'll just interpret those, okay? So let's pop over to the lab.